Hello again, everybody. We're working on Unit 4 now, which is soils, mediums, and plant nutrition. They basically put a bunch of stuff together, basic soil and stuff. And 4-1 is going to be soil features. So let's take a look at what we've got. All right, guys, the objectives we are covering now. First, we're going to examine the physical and hydrological features of the soil. Remember, hydro means water, so actual soil and the water properties. We're going to explain vertical section of the soil going up and down and the 5 horizons of the soil were the different layers. We're going to distinguish between various soil types like clay and silt, loam, and sandy soil. And we're going to explain how pore size, meaning the holes in between the particles, how the pore size is going to dictate field capacity, PYP, PWP, which is permanent wilting point, and SWC, soil water content. I have no idea why they use those abbreviations, but here we go. All right. This time for your objective slides, we have Boozman, we have a crash course. So we have actual, videos rather than just little snippets on YouTube. There might be one snippet, I don't know, but this one, this time we're going to look on the actual slide here for how many film facts you'll be collecting. Okay, it tells you right there. 2, I think, are 15, and 1 is 10. You'll see they're written right here on the individual the new page where we introduce the new objectives. All right, and this first objective, again, is to examine the physical and hydrological features of the soil. So this phrase is talking about analyzing the 2 main aspects of soil, the physical properties and its water-related characteristics. The physical features are going to include the soil's texture, the size of the soil particles like sand, silt, and clay, and the arrangement of those soil particles. We're going to talk about color and density and porosity. Porosity means the holes to hold water. And these things are all going to influence how the soil interacts with plants, affects erosion, and determines its ability to hold nutrients. So all of those things are important with just the physical features of the soil. And then the hydrological features, of course, this pertains to how water moves through the soil, including infiltration, meaning water entering the soil, permeability, how easily the water flows through it, and moisture retention, how much it can hold, and then drainage, of course. Understanding all of these aspects is crucial for maintaining water resources, agricultural practices, and ecosystem health. With us being a plant science course, basically agricultural, but also ecologically, we want to do the best practices ecologically, not just to grow the plants and to feed the people, but to take care of the environment as well. And the best agricultural practices are going to also make sure that the ecosystem stays healthy, and that means not wasting water or damaging water and stuff like that. So examining both the physical and hydrological features are going to give us insights into soil health, its fertility, and the role in the environment. Now, the next objective is to describe the 5 horizons of the soil. You see here with the letters, okay? And there's one down here at the bottom that's not listed. This picture I took from your book. On the next slide, I go over all 5 of them. Okay, first, 1 and 2 is stuck together here on this slide. It's the topsoil, the A and O horizons. All right, they're the uppermost layers, the rich organic behind my head, organic matter, I'm sure, and nutrients where most of the plants grow. So that A and O together makes your topsoil. Then the subsoil is B, okay, down here. It contains minerals leached down from above, and it's usually denser, meaning thicker, but also less fertile. Then you have what down here in C horizon, the parent material. Okay, this is the weathered rock and the minerals that provide the raw materials for the soil foundation. And then way down here is 5 is bedrock. Yes, bedrock, just like Minecraft. Bedrock, which is labeled in this photo, but it wasn't labeled in the last one. That's why that looks so funny right there. But it's the solid rock layer beneath the soil, which can be broken down over time, but it can't be used as it is. It can't be used like this right now. It has to be broken down before it can be used, and that's going to take quite a bit of time. So those are our 5 layers, and I'm going to go over the specifics of each layer next. All right, guys, I stopped the video and adjusted this little bubble thing where my face is, trying to hope that we can still see our picture. All right, so starting off with the O horizon. O stands for organic. All right, that makes good sense. That's why it's up here at the top. Since you would think it'd be alphabetical, but no. All right, O stands for the organic. This is the organic horizon. It's the uppermost layer of the soil, and it's primarily organic material like dead leaves and stuff. So here's the key characteristics of the O horizon. It is mostly decomposed plant material like leaves and twigs and other stuff. It also has a lot of living organisms in it like fungi, bacteria, and insects. So again, this is the organic horizon. The O horizon is typically dark brown or black due to the high concentration of organic matter. The carbon that makes up living things is basically black. And so that's why the top layer of soil is really, really dark. The thickness of the O horizon can vary based on anywhere from a few centimeters, okay, to several decimeters, which I don't know why they're using metrics. Basically 1 or 2 inches to 4 or 5 inches, depending on factors like vegetation type and climate. The thicker the layer, the healthier your soil. And if any of you guys are taking a leaf blower around to blow either dirt or grass clippings or whatever, that is so bad for this layer. A leaf blower is one of the worst things you can do for your soil. Just saying. That's a little bit of my environmental science coming through. All right, so letter D, the biological activity. This layer is very rich in biological activity. There's a lot of stuff going on. It's a habitat for various organisms to help decompose that organic matter, detritivores and decomposers to help return nutrients back to the soil. The importance of this layer on soil health, it is critical. This is one of the most important layers because you are putting nutrients, recycling nutrients back in. So it's very critical for soil fertility and health. It improves the soil structure, enhances nutrient availability, and supports moisture retention. So it keeps it from drying out. If you have a nice thick O layer, when the sun beats down on it, you're going to be able to keep more of your water. It won't all evaporate out. So the role in the ecosystem, the O horizon plays a vital role in ecosystems by contributing to nutrient cycling and supporting plant growth, influencing water retention. It serves as a foundation for the development of other soil layers and is essential for maintaining healthy terrestrial ecosystems. Okay, let me go to the next. All right. Next up is the A horizon. Now we're doing it alphabetically. Okay, it's basically the topsoil. It's the uppermost layer of the soil and crucial for the plant growth. And again, this is not counting the organic stuff just laying on the top of the soil, like leaves and bugs and stuff. They just lay on top of the soil. This is where we're actually getting into the soil. It's the topsoil. Its composition, it's very rich in organic matter because it's so close to the top there, including decomposed leaves, plants, microorganisms, dead stuff, it's all there. It all contributes to the dark color and nutrient content. Again, carbon is black. It's very nutrient rich, very fertile, provides essential nutrients for the plants, making it vital for agriculture and gardening. So again, you have to take care of your topsoil. It's the most important thing in the world to take care of the topsoil. Stay away from leaf blowers. I may say it several more times. Stay away from leaf blowers. They are like the worst thing you can do. All right, biological activity in this layer. It supports a diverse ecosystem of organisms like earthworms and insects and beneficial bacteria, funguses, and stuff that help to break down the organic matter and enhance the soil structure. Water retention. This has good water holding capacity, which allows the plants to access their moisture easily. If you take a look in here, again, this is the A section. This is also where a lot of the plant roots are. So it's important for the plant roots to be able to pick up water at this layer. The thickness of the topsoil can vary, again, depending on location, climate, and land use, but it's generally only a few inches deep. Okay, it's not really very deep, which means we need to protect it. That's why it's so important for us to protect it. Overall, the topsoil is a critical role supporting life, providing nutrients and conditions necessary for plant growth. All right, next layer down. This is the layer B. Look, it's much bigger. Look at that. Well, that's a little bit more than what it is. This right here. This is the B layer. All right. It's called the subsoil. Okay, it lies beneath the topsoil and has several distinct characteristics. The composition of this one is primarily minerals that are leached down from the topsoil. And it often contains clay and iron and other minerals, giving it a denser, more compact structure. With our nutrients here, it may have fewer nutrients in it than the topsoil does because there's less decomposing matter there. The subsoil can accumulate minerals like iron and aluminum oxides, but not really organic stuff, which can affect its color and its fertility. It has a lot less organic matter, like I said, compared to the topsoil. Subsoil has a much lower organic content, resulting in a lighter color and reduced biological activity. So it's going to automatically be lighter when you go down that far. As far as water retention and drainage, this texture and composition, the texture of the soil and what's in it is going to influence how well the soil holds water. The subsoils with a lot of clay in it, which we're going to learn at the tail end of the lesson here, with a lot of clay are going to retain water, but they may drain poorly. So it's quite possible with high clay content to suffocate your plants. Like I said, we'll get to that in a minute. But sandy soils can drain really, really well, but they may drain too fast and not hold enough moisture. So again, when we get to the soil types, we're going to talk about different combinations of those things. With the depth and variability of the subsoil, um, they very widely, depending on factors of climate, vegetation, and land use. As this stuff is going on right here, the faster the water flows through, the faster the decomposition, the faster these rocks evolve. All of those things are going to change the amount of subsoil you have right here. Overall, it's important for supporting the root system. It influences water movement in the soil. And even though it's less biologically active, it's important. There's not a lot of organic stuff going on, but you have a lot of water and mineral stuff going on in the subsurface. See, letter C gets us down to the parent material down here, whatever rocks we're building this soil off of. It's the parent material or the sea horizon. It's the layer of soil that lies beneath the subsoil and these key features. The composition of this one consists of the weathered rock and unconsolidated, meaning it's not stuck together, materials such as gravel, sand, silt, and clay. So just clumps of stuff, not even packed. It serves as a source of minerals as those rocks break down for the overlying soil layers. The formation, so the parent material can originate from various sources, including the bedrock in situ weathering, meaning in that position, it just kind of wears down where it is. Or you may have deposits from glaciers or rivers or wind, and that would be transported material. So you either have in situ, meaning in situation in that place, or transported stuff in there, either way. And the physical properties of the parent material, the texture and structure of the parent material can vary significantly, of course, depending on what you're building it out of, influencing the soil properties above it. For instance, sandy parent material, if it's sandstone, may lead to very well drained soils, while clayey material can result in heavier and more moisture retentive soils. It has very minimal biological activity here, not much going on as far as living things, not this deep. Unlike the topsoil and subsoil, the sea horizon has very little organic matter and very little biological activity, and it's primarily made up of the mineral material. And its role in soil formation over time, the weathering process are going to break down the parent rocks and contribute to the formation of the overlying horizons by supplying minerals and nutrients. And it's still essential for soil development, influencing the characters of the entire soil profile above it. All right, now the last layer, down here to the bedrock. Okay, it's called our horizon. I have no idea why we didn't use D or whatever. It's called the R horizon. It's the deepest layer of all the soil, consists of solid, unweathered rock. Okay, so again, once you get all the way through the soil and down to the rock bottom, that's the bedrock. It's made up of various types of rocks, depending on where you are. If you're like near volcanic activity, or this area used to be under the sea, or whatever it is, would determine. You remember the rock cycle? That'll determine what rocks are there. So you may have granite or limestone or sandstone, and this layer is the foundation of the soil profile. Unlike the layers above, the bedrock is solid and not easily broken down, providing a stable base for the soil above. Over time, I mean Geologic time, this takes forever, okay? Weathering processes can break down the bedrock into smaller particles, and then they become part of the seed file, the sea horizon, contributing to the formation of the layers above. It includes physical weathering like freeze and thaw cycles. I don't know if you've ever noticed, this is why we have so many potholes in the springtime, because of freeze and thaw. Excuse me. And then chemical weathering, like reactions to water and acid. Those things can eventually break down the bedrock layers, and then it will become part of the sea horizon, the parent layers. So the depth of the bedrock can vary significantly depending on location, ranging from a few feet below the surface to many, many meters deep. So it depends on, if you have a good soil up here, the bedrock may be really, really low. But if you don't have much soil, it won't take you long before you get down to the bedrock. As it influences the soil, the type of the bedrock can affect the mineral content and the drainage characteristics of the soil. For example, limestone bedrock can lead to soils very rich in calcium, while granite may produce more acidic soil. Okay, so it depends on what you break it down as to what minerals were in it. Overall, the bedrock plays a critical role in soil formation, and it influences the characteristics of the entire soil profile. All right, here is our next objective. We're going to talk about that clay, silt, loam, and sand. We talked about it a little bit. These are the different types. And we have our next video, okay, right here. This is just a regular soil type video. This isn't like anything cool, I don't think. Um, but this one I want you to get 10 facts off of, all right? Like the last one was 15. Make sure you get them right. This one's 10. So let's see what we have next. Oh, hold on. All right, so again, we're talking about soil types. Clay is going to be our first one. The particle size is very, very small. If you were to try to take it apart to get it in your hands until you can feel a clump of dirt, a single little, like a grain of sand kind of feeling, okay? Clay is very, very small. It's very smooth and sticky when it's wet. You guys know what clay is, right? All right, the Play-Doh, like natural Play-Doh, if you've ever had an art class, a lot of times when they're using clay for ceramics, they actually use clay. Okay, so it's very, very sticky when it's wet and then hard when it's dry. It has very, very high water retention. Okay, it sucks up water really, really well, but it can hold on to it too hard, and then the plants can drown. Especially if they can't. Once you get that sticky stuff going on, the plants can't get their roots through very well, or it will, compact around the roots and it'll kill the plant. So too much clay is not a good idea. It is good to have a little bit because it's great for holding on to moisture, especially in soils in areas where drought is a problem. So it's excellent at holding nutrients because of the high surface area. There's a lot of nutrients that you can have in there. It's good for plants that like moist conditions, but it can be challenging for root growth due to the compactness. Like I said, it'll pack in tight and the roots can't get through. Now, the next one is silt. Can you see this picture? Like if you were to rub this through your fingers like that, you'd feel some of the particles. It's a little bit bigger, and intermediate sized particles. It's soft and smooth, and it kind of feels powdery when it's dry, whereas the other one was sticky and then turned hard. This one kind of feels powdery. It holds moderate amounts of water. It's better than sand. It hold let's do this the right way. It holds moisture better than sand, and it drains better than clay. So it's a good intermediate, okay? Because sand isn't going to hold your water good enough, and clay is going to hold it too hard. So you get silt right here in the middle. All right, it's good nutrient retention, but less than clay, okay, because it is going to drain. It's often found in the floodplains and riverbanks, so it's usually pretty nutritious. Okay, it's ideal for crops due to the balance of moisture and drainage. All right, loam is the next one. Okay, it's a balanced mixture of sand, silt, and clay. Like we talked about the three different kinds, loam is a good combination of all three. It's typically around 40% sand, 40% silt, and 20% clay. Like I said, you don't want too much clay because it packs tight. But if you can mix the clay in with sand and silt, then you can have a really good combination. It's crumbly and fertile and very easy to work with. This would be the good stuff when you go buy a bag of dirt at Home Depot or Lowe's that you're going to put plants in, like house plants. This is the good one. It has moderate water retention, retains moisture well, but it also drains effectively. Like I said, you've got the best of both worlds here. It has good nutrient holding capacity, makes it highly fertile. It's considered the ideal soil for gardening and agriculture due to the balance of texture, drainage, and nutrient content. So, like I said, this is the best combination between it. And the last one is sandy soil. Like I said, we've talked about it good. Again, you know sand, okay? If you were to rub it between your fingers like this, you would definitely feel the grittiness. These are the large particles here. It's very gritty and coarse. It feels rough to the touch. It has very low water retention. It drains very quickly, which can lead to drought conditions in the soil. It's very poor nutrient holding because again, it has large particle size and the water is going to go right through. It is good for drainage. Like if you have a plant that likes to be dry, okay, but it requires frequent watering and fertilizing. Often used for crops that need to be well drained conditions like certain vegetables. Some of the vegetables prefer not to have water on them all the time, but that means you're going to have to water them and feed them pretty often. So here we have our combinations. Okay, we got clay up here, all right, and we've got sand down here. We've got silt over here. Okay, so the best is the combination. Look, there it is, loam in the middle. That is the best combination. Okay, so clay is the high water retention and nutrient rich. The silt down here, okay, this is moderately retains nutrients and it has a lot of sorry, let me try this again. It moderately retains moisture, but it has a lot of nutrients. Silt is usually previously riverbeds and deltas and stuff, so there's a lot of fertility in there. Loam, again, is the ideal balance in the middle of sand, silt, and clay. It's easy to work with. And then the sandy soil is going to drain very quickly and not hold a lot of nutrients, and it has a real gritty texture. Each soil type has unique properties, making them suitable for different types of plants depending on what your plant needs and what you're trying to grow. So knowing that you can combine the three, sand, clay, and silt, into loam, okay, whatever combination you're trying to get going on, and see what you'll do when if you got deep into the agriculture, you'll have somebody say silty clay or silt clay loam or silty loam. Can you see where I'm circling? Maybe I should get yellow. Yellow. All right, like silty loam right here or sandy loam. They actually characterize the soils by this, whatever their combination, sandy clay, okay, silty clay, all right, clay loam. So, um, like I said, as you get it, if you get into agriculture deeper, you'll talk about soil profiles like this. And the profiles, I'm not sure exactly. That might be the right word. It may not be the right word, but they use this as they're discussing the soils. Here is our next objective to explain pore size. Remember, we're talking about that's the holes in between it, how it dictates field capacity and permanent wilting point and soil water content. So these are three things we're going to learn. We're going to learn what field capacity is. We're going to learn what permanent wilting point is, and we're going to learn what soil water content is, and we're going to learn how pore size dictates those three things. And here is your last maybe it might be your last one. This your next, well, your next anyway, your next video. This one is a crash course, so it should be a nice one. I've got 15 facts coming off of this one. All right, so this should be a good one for you. All right, so let's take a look at the next. We're going to start taking apart this pore size. So soil pore size here plays a crucial role in determining field capacity, permanent wilting point, and saturation water content. And so saturation water content first is the maximum amount of water that a soil can hold when all of its pores are filled. You see this? You see how much water there is on this field? It's full. Okay, that's saturated. Okay, all the pores are filled, typically after heavy rainfall or irrigation. And the influence of the pore size, which has larger pores that are found in sandy soils. You know what I mean by pores? That's the space between the particles. So because the particles are big in sand, you're going to have big pores, big spaces, to allow the water to drain quickly, and they don't hold much water. Conversely, the small pores, like in clay, are going to retain the water because remember, clay particles are the tiniest. So they are also going to have the tiniest holes between the particles. They're going to hold a lot more water. So the saturation water content is going to be higher in clayey soils due to the ability to hold water in those fine pores. Now, next one is field capacity. Okay. So field capacity is the next thing we want to talk about. It's the amount of water retained in the soil after the excess water drains. Like the last thing we did was saturated, right? Saturated means too much water. Now, the next is once you've got drained off all the extra, how much is there? This is the field capacity. Okay, so after the excess soil has drained and the soil is no longer saturated, this is the ideal moisture level for crops. This is the field capacity, meaning this is the good amount of water. And so the influence of pore size, field capacity occurs when gravity has drained off all of the excess water, but the smaller pores are still holding some water through the capillary forces. And so the soils with a good balance of pore size, like loam, remember that was the best one, they reach optimal field capacity because they can hold sufficient water for the plant uptake without being waterlogged, because you don't want these plants to be waterlogged. Okay, you want them to be able to take up their water, but you don't want them to be soaking. So in contrast, sandy soils reach field capacity quickly because they hold less water, while clay soils can hold more water but drain slowly, potentially leading to oversaturation. Now the last one is permanent wilting point. Okay, you'll see the poor plants here dried up. So permanent wilting point is the minimum soil moisture level at which plants can no longer extract water, leading to wilting. There's so much of it's gone, there's nothing for them to pull up. At permanent wilting point, the only water held in the very small pores is available to the plants. The larger pores are going to drain too quickly, and once the soil loses moisture to the point where the only small ones have it, then plants are going to struggle to extract it. Clay soils retain moisture longer, but can reach permanent wilting point if the water held in the micropores becomes unavailable, like if it clogs up together. The sandy soils can reach permanent wilting point a lot more quickly because of their low water retention. Remember, it just goes through so fast. Yeah, I'm not sure why this is the exact same slide that we just went through. Let's skip over this one. All right, so let's put together this stuff we've been talking about, the pore size in the soil, how it dictates the field capacity and permanent wilting point and soil water content. So soil water content is high in soils with small pores like clay, low in sandy soils. The field capacity, this is where it's good. This is what you're wanting to have. The optimum water level is held in balance of the pore size, and pore sizes and loamy soils, of course, are the best. The permanent wilting point is critical for understanding when the plants can no longer access their water. They're influenced by small pore size that retain the moisture. So understanding these concepts will help effective soil water management for agriculture and landscaping. So you know how much water to give to your plants and when to overdo it. So this, okay, look at your picture here. This is saturated soil. This is field capacity where the plants can get plenty. This is perfect. All right, and this is getting a little bit low. Do you see where there's spaces in here? They're having it's starting to the field capacity is starting to drop. And at this point, you see that there's still water in the soil. This is the permanent wilting point. There's still water here, but not enough for the plants to get. All right, and that's why it's called the permanent wilting point. All right, so that's, and again, that has to do with pore size. Do you see the little particles that are making up the soil? The pore size means how much the water can fit between how much space there is for the water to fit between the pores, between the holes in the particles. Okay, and I think that's the end of this lesson. All right, I'll see you guys next time.